Good day. Welcome to the Cool Fish channel. So today I'm going to tell you about the topic of magnetic translations on a lattice. So that's our topic for the day. What I'm going to talk about is based on a book by Bernevig and Hughes. But this magnetic translation stuff goes back to the work of Brown and Zach. Okay, so I'm going to use this book by Bernevig and Hughes because they do a particularly good job of this on a lattice. And constructing the magnetic translation group was first done by Brown and Zach in the 60s. I will actually discuss those in later videos as well. So what is the problem that we are dealing with? Actually, this set of problems really gained a lot of traction with the discovery of the quantum Hall effect. So suppose that you have a two-dimensional system and you have a magnetic field pointing outside, perpendicular to the plane that you are on. Okay, and basically you might have a Hamiltonian for that system, which is given by, so let's say, I'm going to set the hopping integral to be 1, okay, but I could write Cm plus 1n dagger Cmn e to the I theta x mn plus mn Cmn plus 1 dagger Cmn e to the I theta y mn. Okay, so this is an x here. This is a y. This is a hopping. So if you have a lattice, okay, two-dimensional lattice, okay, and some particular point is mn, okay. And then in the x direction, let's say this is m plus 1n, you can have an electron hop via this term. So this operator Cmn here annihilates a particle at this particular at lattice site Mn, but this C dagger m plus 1n creates a particle at its next door neighbor in the x direction. Okay, and then we have this operator which does the same thing in the y direction. So here's our site Mn plus 1. Okay. And we also need to add to this to make the Hamiltonian Hermitian the complex conjugate or Hermitian conjugate, sorry, of both of these. Okay, now normally there's a hopping. Okay, so there might be a TA or a TX actually multiplying this term, or a TY multiplying this term. Okay, but for the time being, I want to just keep the notation simple, and I will not add a hopping term. Okay, so this is what our starting Hamiltonian is. And I still have to tell you one more thing, and let me write this a little clearer. Okay, so we have two additional quantities here, this one and this one. Okay, and these are actually the so-called piles phases, which the lattice model picks up when a magnetic field is applied. Okay, and how is this related to the magnetic field? Here I just wrote B perpendicular, so you have a homogeneous magnetic field B perpendicular. Well, what this is actually is the integral of the vector potential along the bond. And for example, this is in the x direction. These are hoppings in the x direction. So it's actually along this bond. And hence here only the x component matters. And so it's the integral of the vector potential along this particular bond. That's what theta x mn is. So it starts at mn and it ends at m plus 1n. Okay, which we can write also like this. So I go m to m plus 1 ax dx, but I keep n fixed. And apologies, I gave you the wrong units. but both of these are multiplied by E over H bar, E over H bar. Okay, and theta YMN is E over H bar M N A Y dy M N plus 1, which we can also write as N N plus 1 AY dy, keeping, in this case, M fixed. Okay, so this is going to be, so what I just gave you is theta y m n along this bond. Theta x m n is along this bond. Okay, now I still have not specified the vector potential. Okay, the only thing I told you though is that there's a homogeneous magnetic field pointing in the let's say z direction, so perpendicular to the plane. So that actually leaves you with only certain specific choices for the vector potential, because you know that B is the curl of A. Okay, and we need a B in the z direction. Okay, a homogeneous B in the z direction. There are several ways to do that. I do not want to specify yet the vector potential. That's going to be done later. Okay, now I will do that later. What I want to focus on is how to construct magnetic translation operators. Okay, so before I specify what the vector potential is going to be, I will go through how to construct these operators. Okay, now, so what is the issue here? You know that there's such a thing as Bloch's theorem, which actually states, so first of all, Bloch's theorem is based on the idea of a translation in real space. Okay, so we have Tx, Ty, and let these be translation operators in the x and y directions. And actually the essence of Bloch's theorem, or what Bloch's theorem states, is that the wave function of a system on a lattice, okay, where you have periodic boundary conditions, takes a particular form because these Tx and Ty operators are symmetry operators of the Hamiltonian. Okay, so if there is no magnetic field, Bloch's theorem is actually relatively simple, right? So we have Tx and Ty are part of the Hamiltonian. They commute with each other. They commute with the Hamiltonian. So one can actually go away and construct the so-called Bloch states, which are the wave functions that one needs. However, when there's a magnetic field pointing in the z direction, one problem is that these operators, which we haven't even constructed yet, but they don't even commute with each other. But let me actually just give you an idea what I mean by considering considering the Hamiltonian. Okay, so let me actually write the Hamiltonian now as Tx plus Ty plus the Hermitian conjugate. Okay, and let me actually just go back to this and tell you that this overall is Tx and this is Ty. Okay, that's Ty. Okay, so that's Tx and that is Ty. Okay, and before I actually even analyze this commutation relation, I have to actually tell you a couple of other things. Okay, so before going down there, let me actually tell you about the lattice derivative. Okay, what do we mean by lattice derivative? So we suppose that we have this quantity theta x mn. Okay, so the x doesn't even matter here. Okay, I'm going to take a lattice derivative in the x direction. So that actually means theta x m plus 1n minus theta x mn. So this is what the lattice derivative means. Similarly, you can take a lattice derivative in the y direction. Okay, so in this case, you're going to keep m fixed. Here we kept n fixed, and we varied m, okay, as much as we can because we are in a lattice, okay? And here we vary, so theta y m n plus 1 minus theta y mn. Okay, so these are the so-called lattice derivatives. And with the lattice derivatives, you can also do the following. This is going to be very important later on, that you can take the x derivative of the y flux, y Pyros flux, minus the y derivative of the x Pyros flux. And in this case, what do we get? Well, we can write this explicitly based on what we have up here. Theta y m plus 1n minus theta y mn minus, so this one now, theta mn plus 1x plus theta mn x. Okay, but this is actually a quantity which we already know. And let me just remind you from the previous sheet how this is defined. Okay, so we have these definitions. So for example, theta y mn is this flux integral, not flux integral, but vector potential integral. Okay, so based on the previous definitions, we can actually write, first we can start with this. So let's start at position mn. Well, this is actually an integral of the vector potential in the x direction, holding n, the y component, fixed from m to m plus 1. Okay, so what this is going to do is make a line integral in that direction to mn plus 1. The other positive term here is this one. Well, here it's in the y direction. This is a y. It's in the y direction. We will keep m plus 1 fixed. I made a mistake, sorry. Let me do this again. So this is actually m holding n fixed to m plus 1 n. Okay, so now we're at this point. Now we do this one. Well, this is in the y direction, holding m plus 1 fixed, and go from n to n plus 1. So now we are here, okay? Then we have this one, which is actually in the x direction, holding n plus 1 fixed from m to n plus 1, but it's negative. Okay, so it's actually this. And this one, by the same token, is actually coming back here. Okay, so overall, this is actually the integral of the vector potential around one plaquette of the square lattice that we are on. Okay, and let us say, sorry, I forgot this. This is E over h bar. Okay, this is multiplied by E over h bar. But we can actually, by way of Stokes theorem, we can write this as the magnetic flux over this area. Okay, or we can also write this as 2 pi times phi, where phi is the number of magnetic flux measured in units of h bar over, not h bar, h over E. Okay, so phi is the magnetic flux measured in units of h over E, h being Planck constant and E is elementary charge. Okay, so so this equation we will need to keep in mind. Okay, but basically the lattice curl, okay, we can say that this is rho theta, okay, rho theta mn, this is the lattice curl. It ends up being 2 pi times the number of elementary fluxes in a particular, in a plaquette of our unit cell. Okay, so let me actually just specify a couple of things. We are in a square lattice, and we took the lattice constant to be 1 in each direction. Okay, so we're going to keep to that just for simplicity. Okay, now before going further, a couple of things. First of all, so our Hamiltonian is in some form like this, right? So it's mn c m plus 1 and c mn, this being a dagger, and e to the I theta x mn plus other terms. Now you can first of all wonder what type of symmetry operators will leave this Hamiltonian invariant. Okay, and I'll just give you that. It turns out that there's a U1 symmetry. If I take C, all the operators, the C operators in my system, and I give it an elementary phase e to the I theta, that actually leaves this Hamiltonian invariant. Okay, so we have a U1 symmetry. Now, my big question though is commutation. So let us play with commutation. Okay, and it's actually rather easy here because what we can do is study position eigenstates. Okay, so for example, CMN dagger operating on the vacuum is a position eigenstate. Okay, so MN. So let me write this here. This is a position eigenstate. Okay, and we can for example, we will take the operator Tx. So let me actually define you again the operator Tx. That's a sum over Mn. Let me call that M prime N prime C M prime. Sorry, this is a plus one. N prime dagger C M prime N prime e to the I theta x M prime N prime. That's our Tx operator. And now the question is, what happens if our Tx operator acts on a position eigenstate? Okay, well, of course, this creation operator will just keep running into vacuum eigenstates, zeros, okay, except at the site Mn, where it will eliminate this creation operator, okay, and then this operator will hit the vacuum, okay, and it will. So this is Cm prime plus 1 N prime, and an M plus 1 N site will be created. Okay, let me actually just make that more convincing. So let me forget about the phase term for the time being. So what is M N prime? M prime N prime rather, sorry, M prime plus 1 N prime dagger C M prime N prime. Okay, and now it's acting on CMN dagger. Okay, so I'm going to use a commutation relation or anti-commutation relation that exists for fermionic operators, right? So that's actually delta M prime. So I can replace this product according to the anti-commutation rules for creation and annihilation operators by M prime delta N prime minus CMN dagger CM prime N prime. Okay, so that's what I can replace this product of operators with. But you see, this is a delta function. Okay, so that just kills the sum, both sums here. This is a creation operator followed by an annihilation operator. But when an annihilation operator hits the vacuum, it's going to give us 0. Okay, so in other words, I ignored the phase again. Okay, but if there is no phase, we're just going to get M plus 1 N. Now I put the phase back. Obviously, we're going to get e to the I theta x M N. Okay, so that's what we get when this Tx operator acts on a position eigenstate. But what we're after is commutators. So let's do some commutators. Okay, so here's my Tx Ty M acting on Mn. Okay, well, the Ty, for the same reason as before, it's just going to give us, so I'm going to let the Ty act first because it's to the right to this Tx. So Ty hits this position eigenstate. I'm going to get M n plus 1 e to the I theta y Mn. Okay, and then Tx hits this. It's going to shift M to M plus 1, and it will give us, sorry, this is theta y. We're going to get M plus 1 N plus 1, and that's multiplied by, I'm going to write it here, e to the I theta x M n plus 1 e to the I theta y M n. Okay, so that's actually when we do Tx Ty. When we do Ty Tx, Well, we can basically read it off following the logic, right? So first, again, here you have a y, so you're going to shift n by 1, and then you're going, after you have m plus m n plus 1, you're going to shift m by 1, so you're going to end up at m plus 1 n plus 1. That's the same thing here, so we're going to end up at, sorry, m plus 1 n plus 1. However, these things will switch directions. In other words, well, not quite. So it's going to be e to the I theta x mn, because that was where our first hopping originated. And then we're going to have e to the I theta y. Well, x took us to m plus 1 n. So here we're going to have m plus 1 n, because the y jump originated at the position m plus 1 n. Okay. Now it's obvious though that although I didn't give you what theta x and theta y are, we're going to do that later. But for an arbitrary theta x and theta y function, tx and ty, which are the operators of our Hamiltonian, do not commute. Okay, so that's actually that's what gives rise to the necessity to reformulate the translation group in these systems. Okay, so I can actually write, based on this, I can concatenate this result as tx ty is equal to ty tx e to the I theta x m n plus 1 e to the I theta y m n e to the minus I theta x m n e to the minus I theta y m plus 1 n. Okay, so in other words, you have to go from this one to this one, so ty tx to tx ty, you have to take these off, so that's what these two do, and you have to add, well, multiply with these to put to the right phases. But the interesting thing is, if you look at these four phases and you add them together, you get something that's actually familiar, because here what you have is theta x m n plus 1 plus theta y m n minus theta x m n minus theta y m plus 1 n, which is actually a lattice curve. The way I actually wrote it, so if this is my site mn, in this case, it's going around like this. It's going around like this, okay? So it's actually the negative flux per placket, per placket, per element, per unit cell. But I guess the way I want to write this is that ty tx is equal to e to the I 2 pi phi times tx ty. Okay, so this is actually a result. Okay, so magnetic translations. This is not the magnetic translation operator yet, but it's related to it. But the hoppings that comprise our model, the x direction and the y direction hoppings do not commute in this case. Okay, so they do not commute in this case, and that's where the challenge originates. Okay, what we want to do actually is to construct magnetic translation operators. Okay, so we want to construct operators which commute with the Hamiltonian. Okay, and we cannot actually do that, but under certain circumstances, we can construct such operators. I'm going to call my operator tx tilde, and I'm going to take it to be of the form mn c m plus 1 n dagger c m n e to the I, and I will add a phase here, which I'm going to call chi x mn. And then likewise, I'm also going to define an operator c dagger m n plus 1 c m n e to the I chi y m n. Okay, so these are my operators. And generically, they don't commute with each other either, but we're more concerned here with whether they commute with the Hamiltonian. Okay. And we're going to try to find the chi x mn's and the chi y mn's to be such that we're doing the best that we can. Okay, so that's the objective here. Okay, so what we can do first of all is to say what happens if I commute tx tilde with tx. Okay, so first of all, I'm going to take tx and tilde and tx and have it act on this particular position eigenstate. Okay, so these are two hoppings in the x direction. The first acts on it, on Mn, the position eigenstate. It's going to give m plus 1 n e to the I theta x mn. The second tx tilde acts, we're going to end up at m plus 2n e to the I theta x mn. That's just a number. It goes along for the ride. E to the I chi x m plus 1 n. If we do it in reverse, it's easy to guess what happens. Again, it's two hoppings in the x direction, so we're going to have m plus 2n. And the phases, these, are going to be, well, the reverse actually, because it's going to be e to the I chi x mn e to the I theta x m plus 1 n. Now, in order for these guys to commute, it's obvious that what has to hold is that theta x mn plus chi x m plus 1 n has to equal chi x mn plus theta x m plus 1 n. And we can convert this into a lattice differential equation, a very simple one. Okay, so here's my equation. I'm going to convert it to a lattice differential equation because I can bring this to this side and this to, so I can exchange these, right? So I can bring this one to the left-hand side, this one to the right-hand side. Well, actually, what I want to do, sorry, that's not what I want to do. I want to bring this over to this side and this over to this side, okay? But it's obvious that what you're going to get is delta x theta x mn is equal to delta x chi x mn. This is our first equation. This is the first lattice differential equation that we derived. Now, I want to write, so this is our unknown. Chi is our unknown, okay? So we didn't specify theta x mn, but that's a given because that's related to the magnetic field, okay? And what we want here is to determine chi as a function of that magnetic field. Chi is entered our magnetic translation operators. So this tilde, okay, is important. These are the magnetic translation operators. They're not the operators which comprise the Hamiltonian. Okay, so the Hamiltonian has theta here, theta x mn and theta y mn, rather than chi. Because that's essential. So we did derive one equation. Okay, now we're going to have to derive 4 more. Okay, so the next equation, let's say tx ty. So we want these guys to commute with each other. So we want tx tilde to commute with ty. Okay, so what's the story? Tx tilde ty acts on the state mn, position eigenstate. Okay, well, let's have tx tilde, ty act first. Tx tilde goes for the right. Well, what's going to happen? I'm going to get a hopping in the y direction. Okay, but our origin or starting point for that hopping, sorry, this is y. Our starting point for that hopping was at mn. Okay, Then I make a second hopping in the x direction. So I have m plus 1, n plus 1, e to the I, theta y mn, e to the I, chi x m n plus 1. Okay, that's following the previous rules. And then we also have ty tx tilde mn. Okay, and obviously that's going to also take us to m1, m plus 1, and n plus 1. But the phases are going to be e to the I chi, well, it's the x direction, and that's from the starting point. That's going to take us to m plus 1 n. And here we have e to the I theta y m plus 1 n. So in this case, in order for these things to commute, sorry, there should have been a question mark there. These guys are not commuting yet, but they do commute if the phases are such that, so I equate these two phases, so these and these, if I equate them, then they do commute. Okay, so in other words, if I read this correctly, I'm going to have, let's say I can say chi x m n is equal to x lattice derivative of y m n. Okay, so that's actually our equation, but I'm not going to leave it in this form. I'm going to go back to my result that I derived earlier. Okay, so I'm going to go back to this result actually. Okay, this result. So delta x theta y mn minus delta y theta x mn is equal to 2 pi times phi. This is what we've shown first or second page. So I can actually replace, I can also write delta y chi x mn as delta y theta x mn plus 2 pi times phi. So this would be our second lattice differential equation, which relates theta and the lattice functions theta x and chi x. Okay, and I'm not going to do all four because it's a rather simple exercise, but I'm going to write you now the four equations that you get. So one of them, the two which we already found, are del x chi x mn is equal to del x theta x mn. Then we have del y chi x mn is equal to del y theta x mn plus 2 pi times phi. And then we also have del x chi y mn. This we didn't find, but you can find by the same methods as used above. Del x theta y mn minus 2 pi times phi. And we will also have, sort of symmetric actually, del y chi y mn is equal to del y theta y mn. Okay, so these four lattice differential equations, they relate chi and theta. Okay, so they relate the lattice functions chi and theta, and they have an easy solution. Okay, so you can easily check that if I take chi x mn to be theta x mn plus 2 pi phi times n, that will actually solve this. Okay, and we can also say that chi y mn is theta y mn minus 2 pi phi times m. Okay, so let me actually just show you why this works. I'm going to show you with this one, and I'm going to substitute it into this equation. Okay, so if I take a lattice derivative, so I'm going to take a chi y chi x mn, and that's going to equal del y theta x mn. Okay, and if I doesn't matter if I keep fixed, it doesn't. So this 2 pi phi n is not a function of m, but if I take its lattice derivative in the y direction, it's going to be 2 pi phi n plus 1 minus 2 pi phi times n. Okay, so it becomes del y theta x mn plus 2 pi phi. Okay, so delta y chi x mn is indeed like this. Okay, so that's just a little verification. So now we actually know what kind of chi's to choose. If we know theta, what kind of chi's to choose so that we have magnetic translation operators. Okay, let us now choose a gauge for our system. Okay, so I'm going to now say that theta x m n. So we have to specify these two quantities to proceed. Okay, and the way I'm going to specify it is, well, I can, for example, take a to be 0, bx 0, right? So if I do that, the curl of a is easy to show that it gives me b in the z direction. Because if I take this is actually I think this is called the Landau gauge, right? And the other thing is, so basically now using this based on this we have this was actually not given in lattice variables. Okay, but if we go to lattice variables, first what I want though is that a flux, so units, I took the lattice constant to be 1. Okay, so b actually equals b sorry, the flux, let's say capital phi, is actually b times 1 by 1, so it's actually equal to b. Okay, so we can easily convert this into flux. And remember that our phi flux was this thing in units of E over H. Okay, but the other thing that I want is, okay, so for example, theta x m n is, well, that has to be 0, right? Because there's no x component here. This would be the a x dx holding n fixed, let's say holding n fixed, but m goes from the x variable goes from m to m plus 1. Okay, so that's 0. And theta y m n is actually going to be integrate a y dy, keeping the x component fixed, and the x component is m, and this integral goes from n to n plus 1. Okay, so obviously this is going to be b times m. Okay, or 2 pi phi times m if you go to flux variables. Okay, because this is so b is the magnetic field, but b times 1 times 1 is the flux. Okay, so we have chosen our gauge. Okay, and now let's go and determine chi x and chi y. Okay, so once we have chosen our gauge, so theta x mn, theta y mn is known, and then we have to actually substitute in these equations to get our chi's. Okay, so let me do chi x mn. Well, that's chi x mn is theta x mn, and theta x mn is 0 plus 2 pi phi times n. Okay, so that's so our chi x in our magnetic translation operating in the x direction is going to be 2 pi phi times n. What about chi y? Chi y mn is going to be theta y mn minus 2 pi phi m, right? So theta y mn is 2 pi phi m minus 2 pi phi m, so this is going to be 0. Okay, so it's just sort of interesting that we, in our gauge, the x hopping, okay, so in our gauge, the x hopping has a 0 phase, pios phase. The y hopping has a 2 pi phi m pios phase. And sort of the reverse when you go to the actual magnetic translation operators. Okay, so we found the magnetic translation operator, but now we have to use it. Okay, so let me actually just give us the magnetic translation operator based on what we found. Okay, so we have Tx prime, sorry, tilde, and Tx tilde is Mn Cm plus 1n dagger Cmn e to the I 2 pi phi n. At the same time, we also find that Ty tilde is just an ordinary hopping operator in the y direction. So it's like this. Okay, so these are our two operators, Tx tilde and Ty tilde. Okay, 2 pi phi times n. I hope that's readable. That's a phi. Now I may have made it less readable. I'm sorry about that. Okay. And now the point is that now the question is, do these operators commute with the Hamiltonian? Okay, and Ty obviously does. Okay, so Ty commutes with both Tx, Ty tilde rather does. It commutes with Ty and Tx, but actually turns out that Tx tilde does not. But let's first commute them with each other. Okay, so Tx tilde, Ty tilde acting on Mn. So that's going to give us Mn plus 1. Okay. Um, and so Tx tilde, what is that going to give us? Well, that's going to give us M plus 1, N plus 1, e to the I 2 pi phi times N plus 1. Okay. Ty tilde, Tx tilde, Mn obviously gives us M plus 1, N plus 1, e to the I 2 pi times phi times N. Okay, so these guys, how do they commute with each other? Well, Tx tilde, Ty tilde is equal to Ty tilde, Tx tilde. Let me put it on this side, e to the I 2 pi times phi. Okay, so this is their commutation relation among each other. Okay, but it's obvious actually that if I choose phi to be p over q, where p and q are co-prime pair integers, okay, then tx to the q will commute with ty. Okay, so if I push this, well, this shifts my lattice by units in x and y directions. If I shift the lattice using this operator Tx tilde and taking a phi to be of the form p over q, if I shift it q times, okay, then this will give me 2 pi times p. Okay, so it will give me an identity because e to the I times 2 pi times p is an identity, and Tx tilde and Ty tilde will commute with each other. Okay, and similarly, you can show that Tx tilde q and Ty tilde commutes with the Hamiltonian as well. Okay, so let's summarize what we found. So we have H, which is our Hamiltonian, which commutes with Tx tilde q and Ty tilde. Okay, so that's actually what we found, which means that these two operators are part of the group of the Hamiltonian. Okay, so we didn't worry about other symmetries here, but we have translational symmetry in the following sense, that we have chosen phi to be p over q. We have chosen our gauge to be of a particular kind, okay, right? So we only had a flux, a Pios phase in the y direction, not unhoppings in the x direction. And what we found is that our Hamiltonian commutes with these two operators. And the point is that this means that there's some, we can actually define a magnetic unit cell Okay, and this magnetic unit cell is going to so it's going, what this magnetic unit cell is going to do is it's going to be in the x direction. It's going to be enlarged by a number q, and nothing will happen to it in the y direction. So here in this direction, its length is still going to be 1. So magnetic unit cell is q times 1. That's its dimension. Okay, and then what one expects actually is that if there's a Brillouin zone in the x direction, it has to shrink by a factor of q. So the Brillouin zone will rescale, so will be rescaled by a factor of 1 over q. Okay, but we're going to show this. Okay, so now what do these operators do? Okay, so on particular states. Okay, so for example, if I take t y acting on m n, well, that's simple because t tilde y rather doesn't have any kind of phase, so it's just going to give me m n plus 1. If tx tilde acts on mn, that's going to give me m plus 1 n e to the I 2 pi times phi. Okay, but if I have this act q times on mn, then I'm going to get m plus q n, and that's all I'm going to get, right? Because we took phi to be p over q, and I'm just going to get this phase factor q times, which is 1. Okay, so that's how our magnetic translation operators work. And now there's one other interesting we can say about it is since these guys commute with the Hamiltonian, so h t x q and t tilde x q and t tilde y commute with the Hamiltonian, they have common eigenstates. Okay, so for example, we have one eigenstate of the Hamiltonian would be ek kx ky, because I'm going to attach two labels to the well, there's also the energy label, which I'm not attaching, but I can attach the label kx and ky to the Hamiltonian. It turns out that we can show that in this case there will be a q-fold degeneracy, and this follows from the form of the translation operators. Okay, so we can say the following. So suppose that I let ty tilde operate on tx tilde kx ky. But sorry, before I go here, let me actually cross this. I have to tell you what tx tilde does to kx and k to this particular state. So tx tilde kx ky. Well, we don't know what that does, but tx tilde to the q kx ky is going to give you e to the I kx times q kx ky. Okay, and we also know that ty tilde kx ky is going to give you e to the I ky kx ky. Okay, so and based on this, that's why we can show that there will be a q-fold degeneracy. So let us do that also. So I'm going to take a state tx tilde kx ky. I'm going to operate on this state with the operator ty tilde. And we know what happens if we commute ty tilde with tx tilde. That's going to give us e to the minus I 2 pi phi, where phi is p over q, t x tilde. So I'm commuting them first, ty tilde kx ky. But I know what I know what ty tilde does to ty tilde does to kx ky. it just gives me an e to the I ky. Okay, so it gives me an e to the I ky. So I'm going to have here e to the I ky minus 2 pi times phi tx tilde kx ky. Okay, so what did we find? If I consider this as a state, then ty acts on this state, and it gives me the same state back, so it's an eigenstate, with an eigenvalue of e to the I ky minus 2 pi phi. Okay, so in other words, tx tilde kx ky is an eigenstate of ty tilde with eigenvalue e to the I ky minus 2 pi phi. Okay, and now of course, if we put here some other integer, so if I take a state txm m kx ky, okay, then this is going to give me, so, and if I operate on this particular state with ty, I can commute this m times if I want, okay, and then I'm going to get e to the I ky minus 2 pi phi m times the state back t x tilde m kx ky. Okay, but if m, so m, the only distinct eigenvalues, distinct states are going to be when m is 0, 1 to q, up to q minus 1. Okay, so what we have just shown is that, and these are all states with the same energy, because tx to the q and ty tilde commute with the Hamiltonian. So these are all states with the same energy. So we are going to have a q-fold degeneracy, and we were able to prove this too. Okay, so thank you very much for your attention. This is what I have for today. And in other videos, I will elaborate on this, but I will actually also go into the magnetic translation group as a whole. Okay, so let me actually just say a couple of words about that. So here we focused on nearest neighbor hopping operators, but the full translation group of any lattice has to include all the different hoppings. Okay, and translations from between any of the lattice sites that we have. Okay, so we're going to deal with that in other videos. Thank you very much for your attention, and I hope you enjoyed this little information.